Right, I'm not sure how many people were at the last talk that I gave, which was a few years ago, so I'm quickly going to go through some background on HPSDR. Basically, it's just a group of amateur radio enthusiasts worldwide that wanted to try to build a high-performance software-defined radio, hence HPSDR. And it is a wide world group, but there's people in Australia, USA, all over Europe, and in the UK that are working on both hardware and software development for this product. When I gave the talk before, version 1 was a group of separate boards. So a radio consisted of basically a bus, a passive bus, I should add, 6 slots, and had a AT power connector, so you could use an AT power supply for it. And then there were a bunch of cards, and let's see if I got these in the right order. No. Initially, we had a USB interface, but it was quickly decided that we didn't have the throughput on that. So we replaced that with a Ethernet interface. Now, what you'll notice on each of these boards, there is an FPGA. So all these boards are programmable. So the bus protocols, the actual functionality of the board can be modified. So to build a radio with these, we started off plugging in our Ethernet or USB interface. Then we had a receiver card. And this is one of the receivers. This has got a little extra switch on it, so I can switch in and out a filter on it. And in fact, we could plug in multiples of these. So we could have multiple receivers. In fact, it would support in the firmware up to 6 of these, but we never actually built a bus board big enough to put 6 on. And basically, this receiver has a A to D converter, and it's converting basically 0 to 65 megahertz, taking it all in 16-bit samples and feeding it in, and the FPGA is doing some processing on it. And then similarly, we had another board to make up a transceiver, which is a small exciter board that is 500 milliwatt output. And there's 2 versions of it. Penelope was the original one. Some of these names of these boards were made up by the people that designed the boards. The second version is called Penny Lane. It has slightly different control of how you generate the output power on it. The initial one was based on the level of the IQ data being fed into it. On the Penny Lane one, there's actually a control, so you can have a value between 0 and 255 to set up what output power you want coming out. And you always drive it at the maximum audio level. So this is what we started off with, which then needed to be connected into some filters for receive and transmit, and also had some switching on it for switching multiple antennas into the device. And basically, the switching was automated, so when you send a frequency information to the radio, it then translated that into control signals out to these filters that connect into this. So with that, and then with an amplifier on the top, you could build a radio. So eventually we ended up with a radio which was in a box, sort of like this, way, way too big. So the next effort was to build a single board. And I don't have a Hermes built here, but this was the original Hermes board. And it was manufactured and it was sold either as a bare board for people to build their own, or there was a group that set up that were manufacturing it with all the components on, so you could buy it as a complete board. And it actually is still available today, either as a bare board or manufactured. And basically, this is, if you like, a combination of these 3 boards and the bus onto a single card with a single larger FPGA. Okay. Right, I just wanted to mention TAPA, which is Tucson Amateur Packet Radio Group. They're the original group that developed packet radio, for ham radio. They now work more in the sense that they provide funding for development of different hardware, software projects for amateur radio. And they provided a lot of the funding to get these designed and built originally. And as a result, they then manufactured some boards and sold them to recoup the cost of doing that and also to build up their funds as well. Once they finished doing that, basically the whole thing became open and anybody could manufacture them. As it happens, only one company has really picked that up. There's a company called Apache Labs. They're in India. They were involved in helping some of the design of this stuff. But they have now taken up manufacturing the Hermes cards, and you can buy one of these bare boards from them, and also a fully populated one. But they've also gone on and they're now producing radios that you can buy in ham radio stores. Just to see the sort of thing they've done, they've got one they call the ANAN 10, which is a 10-watt output power, and an ANAN 100, which is 100-watt output power, all based on this board in there, but with the additional filters, power amplifier, and antenna switching capability in them. All this is still all open source, so all the software, the firmware for the FPGAs, all the software that runs on a PC or whatever, and the hardware designs are still all open source. It's all available online for anybody to download, access, and even manufacture your own boards if you wanted to. One of the things that Apache Labs have been doing is actually enhancing what we've got. So they've come up with the model 100D, the D meaning dual receivers. So in this one, we've got a transmit connector here, but we've got 2 totally separate receiver inputs on there. And this was really done initially because of some work going on to have a diversity receiving. So you have 2 antennas, you receive the same signal on each, and then you process it to get the best signal, if you like, out of it. And they've recently come out with a newer version, which is the 200D. This is almost identical to the 100D, except it's using a new Orion card, and this actually is one of the Orion cards. Currently, this isn't available to buy separately from the 200D, but at some point, I'm sure they're going to make it available. But this similarly has the transmit and 2 independent receivers, but now it's also got an additional header where it's possible to add a 3rd receiver to it. And there's some work going on at looking at how we can do, with 3 antennas, basically beam steering on receive for that. And it's also got a larger FPGA. Whether we're going to make a lot of use of that extra space, I don't know at the moment, because there's some work going on in trying to move some of the code off of the FPGA. The FPGA in these is fairly complex code in the sense that it's doing the processing of the A to D conversion and generating INQ data to go out. And then it's extracting out of that 65 megahertz a small section of the bandwidth. So typically it's 4.8, 9.6, 19.2, or 38 4K bandwidth. And that's really to match some of the old stuff that used to be around when we were using sound cards to sample this data as the A to D. But we have been playing with some code on here that is actually using the gig Ethernet interface and pretty well using it all up, trying to transfer everything over the gig Ethernet, the whole 65 megahertz samples, and then doing all the processing on a PC. But for that, we've been doing some work with some of the CUDA cores for all the FFT processing. Not sure where that's going to go yet, but that's still in a sort of a work in process.
Isn't that a problem with 65 gigahertz? I have IQ channels at 65 megahertz. Stability said gigabit Ethernet has 100 megabytes a second, so it sounds like a problem.
Yeah, we're right on the limit with that at the moment. We are looking at using a different interface to transfer that data and design some new cards.
So more likely have like 30, 40 megahertz.
Yeah, but at the moment it's just something we're playing with. Whether we actually do anything with it, I'm not sure. And also, they've just come out with another smaller radio. They call it the 10E. It's based on Hermes, but has a small FPGA to reduce cost, so it's a lower cost radio. I noticed here I said it supports 2 receivers in the FPGA. Even with a single antenna, we can support up to 7 receivers in different chunks out of that 65 megahertz, all running concurrently. Okay, one other thing that's come out recently was somebody was looking at, could we take the firmware that we've developed for Hermes and come up with a device that's a lot cheaper and a lot smaller. So they came up with Hermes Lite. Now this is using a analog devices broadband modem chip in it for the front end. And as you can see, it's a very small, simple card. The idea was to try to build a complete transceiver for less than $150. And so the FPGA, they're using one of these B micro development boards. And basically, this just plugs into that. There's a small board that's really just providing the interface for the antennas. And then you can also buy just a Ethernet interface, plug that in. I think it goes on those pins. And with some modified code from the Hermes FPGA code, this actually connects and just looks like a Hermes board to the software. But it's a bit of a sort of a combination at the moment. And you can only get the bare board, so you'd have to assemble this yourself. But it's not certainly nowhere as hard as assembling the FPGA on the other boards. Okay, let's look at software now. Basically, all the original software was written using a DSP engine called DTTSP. This was written by Frank Brickell and Bob, I've forgotten his last name, sorry, in the States. And pretty well everything used that. And there was a version of that that ran on Windows and ran on Linux. Then Flex Radio, who also manufacture and sell software-defined radios, they developed in the open source world an application called PowerSDR. And that used DTTSP as its DSP engine. For some reason, whatever reason, Flex have now moved on and are developing software and hardware, but it's all closed. They've not made it open anymore. But PowerSDR has continued for OpenHPSDR. It has been enhanced and it's been modified. And more recently, a new DSP engine was developed, which is currently called WDSP, and it has been modified to work with that. And I'll go into that a little bit more in a minute. But as you can see, there's several other things there. GHPSDR was a Linux application that I originally wrote, which uses the GTK toolkit. GHPSDR3, there's no 2 there because 2 got thrown away. It's also Linux-based, but it's a server-client architecture. And that has been picked up by basically another group which does a lot of work with software-defined radios called SoftRox. And basically, they were built originally to provide a cheap radio to do some research with. And they are very cheap, very simple. But basically, I developed GHPSDR3 really to start testing the multiple receiver capabilities we had with HPSDR. And so it has a server that basically takes the IQ stream, splits it out into each of the receivers, and then provides an interface so a DSP engine can connect to those and do the processing. And then there's some clients that run on different devices. KISS console was something else that was written early on, is in C#, and is really meant to be a application that other people can take, and it's fairly straightforward to look at, understand how this works, and possibly modify it for their own requirements. Heterodyne for the Mac. I don't think that's being supported anymore. I haven't seen any enhancements to that recently. QSDR is Windows and Linux. And then OpenHPSDR for the Android is something that I've recently written. And it's a version of the code that will run on an Android device, works within a LAN, not on the wide area network, but directly connects to the radio and does all the processing in the Android device itself. So let's see, I talked about DTTSP. WDSP, a little bit more about that. This was developed by William Pratt, and it was to support his development originally of the diversity code. He found it very difficult to go into DTTSP and add all the additional stuff that he needed. So he started from scratch again, writing a whole DSP engine. And also, he has implemented in there something new called Pure Signal, which I'll come on to in a minute. It's now the DSP engine used in the latest PowerSDR for HPSDR, and I did a port of it to Linux and to run on the Android device, so that's what I'm now using in the Android application. What I should say, when Bill wrote that, he's written it for Windows, so he's used all Windows threading and Windows semaphore code. So I've had to go in and do quite a bit of analysis, first of all to understand what they were, and then to write some code so that we could compile it and run it on Linux and Android. So PowerSDR, fairly complex display, has all the bells and whistles and buttons that everybody would want. now a special version really that supports HPSDR only. It's not very backwards compatible to Flex software. Handles multiple receivers, diversity receivers, and pure signal. So pure signal. Concept of that is that a received signal is taken back in of the output signal that we're transmitting, and then the code dynamically changes the generated IQ samples to improve the IMD distortion. Yeah, quite complex system, but if you can see here, a two-tone test at 30 watts, and you can see how much it's reduced these signals. And it dynamically does it on the fly. So it's listening to basically what you're transmitting and adjusting the IQ output to generate the best signal that we can get out. So basically, to somebody else listening to a HPSDR radio that's running pure signal, it will seem very, very clean when you look at it.
Can you improve the quality of the receiving signal with that also?
Well, because the generated signal is much cleaner, it's basically reducing interference outside your... And I mean, basically, you know, the handbands these days are quite crowded. And that was the idea of it, to try to reduce that interference between signals. This is the first version of GHPSDR that I wrote. One of the things you'll notice here, you can't really see it very well, but that is a band scope of the full 65 megahertz being displayed. At the same time, we're receiving some other set of frequencies. So the FPGA has got code in it to send both IQ signals for the selected band that you're looking at, but it also can send you samples so that you can display a full band scope of the whole 65 megahertz. And that's also available in the Lite version as well. So GHPSDR 3 was developed in C for Linux using DTTSP originally, and it is a client server. Several different clients are available. One that runs on Windows and Linux. It's written in Qt, so it's fairly portable, and it runs across the internet. And there's also an Android client called GLSDR, free to download. You can then select whatever servers are available online at the time and tune around. If somebody else is already connected into it, the first person is the master, anybody else is the slave, so you can't change the tuning, but you can see what somebody else is listening. When the master drops out, the next slave gets master. So, and also has transmit capability, but there's some configuration obviously required to set up that you're allowed to transmit with passwords and whatever. KISS console, as I said, was developed in C#. It's fairly simple code. It was really implemented as a learning device for others. And as you can see, the display is fairly straightforward and doesn't necessarily support all the features. How am I doing, time-wise? Okay. QSDR is written in C++ using Qt framework. It's currently receive only. And a version has also been implemented using the CUDA APIs for the DSP processing. And this has actually got some really nice graphics on it. It looks, a lot more professional, if you like. And then OpenHPSDR for the Android. It's a basic transceiver written in Java, obviously, because it's the Android devices. Uses a ported version of WDSP, and which in its self it uses FFTW3, which is the open source FFT program. So both ported to run on Android, and it runs on Android phones, tablets, and single board computers. That was screen grabbed off my Nexus 7, and it works really well on Nexus 7. And as you can see, it's got a pan adapter display, waterfall display, and it's also got the band scope for the whole 60-odd megahertz. What you'll notice here is there's not really any signals outside of the current band I'm on because it's switched the filters in, so it's filtering everything else out. And as I say, that only works over the LAN because it is talking directly to the radio. The FPGA code in the radio itself supports TCP/IP and UDP, but it doesn't support routing. So you can't route this stuff over the internet, but then the bandwidth, the sampling rate and the bandwidth requirement to go across the internet is probably a little too high at the moment. Okay, so I've got time for some questions, a couple of minutes. I've got a list of links that people could look at if they're interested. OpenHPSDR.org, Tapper.org. The source code for everything is on svn.tapper.org. If you just go in there, you can go on web interface to it. You can go in there, you can plow through quite a lot of different people's attempts at source code on there. The Hermes Lite is on GitHub, both the software design, software code, and the hardware design is all there. Gerber files if you want to produce your own boards, everything. The GHPSDR3 stuff is on that site, and that gives you a lot of information, and you can download all the source code for that off there, including the Android client. And then the bottom one is my blog, where I give updates whenever I can on what I'm doing or what's been going on.